Hi everybody, John Chilko again. What I've done for you is I put together a little presentation that is an overview of the Engine 1420 lab. This is kind of a full deal where you're going to see everything we do in the lab. Throughout the process, we are going to record a little video so you can actually see each step along the way. This is something you would do in person if you were here. Again, this lab is going to involve the fabrication of ceramic composites. Again, ceramic composites very, very useful for many reasons. I'm sure you discussed in class. Wear resistance, the fact that they're corrosion proof, very, very, very hard. Non-conductive properties. If you're using metal, sometimes you'll get a spark if you're near a fuel source. So this is great to use when you're using fuel, impellers, and stuff like that. So what we're going to be doing is we're going to be making one particular type of ceramic composite. And believe it or not, we're going to start with a white powder alumina oxide. You might remember from Engine 41 days that you actually use this stuff to polish your 4140 steel. This is the same exact powder. The particle size we use is extremely, extremely small. It's 0.05 microns, so it's very, very, very tiny. And what we're going to do is we're basically going to compress this together like a snowball, and we're going to try to make a ceramic composite out of it, going through a series of steps. What you see in the bottom corner over here, this is actually an SEM picture of an alumina puck I pressed together. And this is taking in the scanning electron microscope, so you're actually looking at size in nanometers. But I just want to point out that you notice these little openings here. These are all pores, and this porosity is going to play an important role in a couple of different functions along the way as we go through this. So the ceramic composite that we're going to be making is a substance called ZTA, which is known as zirconium toughened alumina. And zirconium toughened alumina is just that. It's alumina, which we're going to stick a little bit of zirconium oxide in and try to make tougher. This stuff, and again, you can see again an SEM picture. What you're looking at in the darker images are particles of alumina, and the lighter images are your zirconium. And you still see some porosity involved here. But the cool thing about zirconium oxide is by adding zirconium oxide to alumina, you actually make it 20 to 30% tougher. High strength, fracture toughness, increased hardness, more wear resistance. There's many, many, many features that are very positive when you do this. One very, very cool thing that Professor Sheldon is going to talk about, and again, you can see a better SEM picture. I wish that my samples actually look like this. Here you can see a perfectly sintered sample. When I say sintered, I'm talking about heating to very, very high temperatures. But you notice that here you don't see any porosity. And unfortunately, with oven temperatures that I'm going to be dealing with, we won't get samples as good. But the cool thing about this substance is it's, and again, Professor Sheldon will mention this, it undergoes something called transform toughening or transformation toughening. It's kind of self-healing. So when you put a lot of stress on this stuff, it actually ends up healing itself. And the way it does this is it actually undergoes a phase switch from tetragonal to monoclinic. And this actually allows the material to actually heal itself before it starts breaking. So very, very cool stuff. We are going to make this through a journey. And the journey is going to start by producing these samples, which we like to call green bodies. And what green bodies are, basically we're going to use this graphite mold, and we're going to stick some alumina oxide particle down each of these little shafts, and we're going to compress it, basically using this hydraulic press. And again, we're going to try to take a snowball and make a very, very, very well-packed puck of this aluminum oxide. So when we do this, we'll press it together, and eventually we're going to do something called pre-sintering. As you would imagine, these are pretty fragile when they come out. It's basically small particles of aluminum oxide just pressed together. So we pre-sinter it, and by pre-sintering, we actually heat these things to 950 C for about 4 hours. And what you end up with is you end up with a little puck, which is a lot better, a little easier to handle of zirconium oxide. So again, we've turned the powder into this little tiny disc right here as we go along. So we're going to make this stuff, ZTA, two different ways. The first way is we're going to do a powder mix. Professor Sheldon in your lab has basically given you different proportions of zirconium oxide. We're going to make a series of samples, but one sample is going to have a little bit more zirconium oxide, the other a little bit less. And one of the ways we do this is we actually are going to make powder mixes of the two powders. So again, we're going to start with alumina. We're going to use a material called polyvinyl alcohol. And why we add just a little trace amount of this is because the alumina is very, very, very fragile. It's kind of like making a snowball with dry snow. It's not going to clump together. You add a little water to it, it sticks a little better. You can kind of think of the polyvinyl alcohol as that water. It's a good bonding agent. We don't have to worry about it mixing up anything or adding anything, because when we heat this stuff up, it should evaporate right out of the little bit we use. And we're going to take some zirconium oxide powder. Alumina, zirconium oxide, a little bit of polyvinyl alcohol. And we're going to mix this stuff for 24 hours in a jar mill. We're going to roll it around. You'll see this in a short video. I have little ceramic cylinders in here, which are going to help mix the powders together. And when we're done, we're going to go back to the graphite mold and we'll press this stuff together. And so I'm going to actually end up making a puck, not just of aluminum oxide, but of aluminum oxide and the zirconium oxide mixed together. That's one of the models that we are going to make for powder mix. The second way, a little trickier, not an exact science, and for 5 years doing this lab, I've tried to perfect it, but it still leaves room for actual improvement, is liquid infiltration. So we will start again with alumina, but this time what we're going to do is we're going to take those green bodies we made in the second slide, just of aluminum oxide, and we're going to infiltrate a precursor, which is basically alcohol and zirconium oxide in a liquid form. And we're going to soak these things together through capillary action and hopefully absorb a certain amount of zirconium oxide that mirrors the amounts that we have in our powder forms. Again, kind of tricky to get the right amount when you do these things, as you'll see. So with the liquid infiltration part of this, again, there's our precursor. We are going to soak our disc, again, our green body, about halfway in this solution. Okay, so again, half in, half out. I've tried different mechanisms in doing this. We've let it sit for 30 minutes and just through capillary action, pull it in, hopefully in all the pores. I've actually tried using a vacuum bell jar where we actually suck some of the air out of the discs and hopefully pull this in at a quicker rate. Regardless of how we end up doing this to get the right amounts, when we're done, we are actually going to take the disc out of the liquid and flip it over, put it on a hot plate for a little bit, low temperature, and try to evaporate off some of that alcohol in that precursor and let it dry. And then when we're done, we actually will take and do the reverse. The side that was sticking up will then go down in the liquid and vice versa. So we'll do the other side similarly. And hopefully we'll end up with a disc that's absorbed the zirconium oxide through this liquid infiltration process kind of the same way as we actually do this. Again, the thing that's kind of tricky about this, if you do this and you wait 24 hours for your puck to dry and you weigh the thing, you might say, oh, Don, I don't have enough zirconium oxide. You have to repeat the process. Now, if you have too much, unfortunately, what that means is you either have to restart with another disc, or you could actually stick it in the furnace a little bit, try to, see if you can heat off some more of that alcohol and see if you can come up with a better mix. But again, the goal is simply to have zirconium oxide absorbed in your aluminum oxide when you do this. So both processes of powder mixing as well as the liquid infiltration, the final step, or one of the final steps, is a higher temperature sintering. And again, sintering, heating at high temperatures, we're going to take these discs and we're going to stick them in this oven, which is up in the ERC, and we're going to heat them at 1500 degrees C for 4 hours. Again, you might remember those pictures I showed you at the beginning where I was telling you I wish my samples looked like this. Again, in a perfect world, I'd be able to heat up around 1700. Unfortunately, I don't have access to a furnace right now that can heat that much, so our samples won't look quite as crisp as those when we see the scanning electron microscope images. After 4 hours, we're going to pull these samples out. And the first thing you're going to notice is that after the 1500 degree 4 hour sintering, your sample has become a lot smaller. Again, here's our original puck, okay? And you notice I have this glued to an aluminum puck. And the reason why this is glued with a substance called crystal bond, because we have to polish this, and there's just no other way to hold it. But again, just to show you the size difference with just the sintering fact as we actually do this, okay? We end up doing this and it works very, very nicely. We're going to end up polishing these things, kind of the same way your 41 samples were polished way back when. We're going to start by grinding, and again, just a reminder about grinding. These grinding stations that I have in my materials lab, different grits of sandpaper starts at 120, 240, 400, 600. A reminder that the higher the number on a sandpaper, again, the finer the grit. We don't need to start way down here. We are going to actually jump to 600. And I'm just going to gently go back and forth and polish my sample. Eventually, I'm going to go to 800 grit sandpaper, even finer. And I actually will finish it with 1200 grit sandpaper. Again, 1200 grit sandpaper is so fine that these little abrasive pieces measure about 8 microns. Very, very, very fine material. Feels like a piece of paper if you could feel it in person. But we're still not done. Even at 8 micron polishing, we have to go even smaller. Unlike the samples you did in Engine 41 where you actually used alumina to polish the samples, we're going to use a diamond slurry. We're going to use a diamond slurry along with an automated polisher. And the diamond slurry starts out 9 micron abrasive pieces to 3 microns down to 1. And the great thing about an auto polisher is that I just have to set it for a time, give it the time that it's going to squirt out the liquid, and I can come back and check my samples later on. So hopefully through this polishing mechanism, we end up with a sample that's really, really clean, shiny, and polished. Okay? And so again, one of the final steps we have to do, if you remember back to 41, before you got images of your 4140 steel, we had to etch, and we ended up using a substance called nitol, a mixture of methyl alcohol and nitric acid. For the ceramic pieces, we found out that we can actually do this just by heating. We're not going to heat way back up to the temperatures we had, but we're going to thermal etch. We're going to go to about 1380 degrees C for just 30 minutes, and believe it or not, this is going to bring out some of the images that we want to see. And our final step will be to take these samples. I'm going to actually end up cutting the samples in half by using a diamond saw, a wet saw. And these are what my sample is going to actually look like. So again, here is a piece that I've actually cut. And the reason why I cut these things is we also want to look at a fractured piece on the inside. So if you look at my image that I have over here, what you're looking at is we're going to be looking at this side, and this guy here is a fractured piece that I actually broke off. We have these little tiny plastic clips that are going to hold the sample in place. And so what we end up with is we end up with a little ceramic piece being held by the plastic clip. Now, one thing I want to point out to you, these are going to be viewed in the scanning electron microscope. And the scanning electron microscope depends on conductivity. You have a sample that's not conductive, right? So again, what we have to do is two things. We carbon coat, we spray a little bit of carbon on these samples as well, or sometimes we just use a little sticky sample on at the bottom, just to give some conductivity for our scanning electron microscope. But we also use this copper foil, which we actually are going to ground so our signal has something to go through. So that's kind of what you're looking through. Tony McCormick, who runs the scanning electron microscope, will do a better job explaining this when he shows you this in a future video. But the scanning electron microscope is where our journey is going to end. We are going to look at our samples, and hopefully we'll see differences in all the samples. Obviously, I'll show you a green body, just the alumina itself. We'll look at the powder mixes in 2 different ratios, and we will look at the liquid infiltration in 2 different ratios, and you'll get these images. Regarding this lab, most of the lab, obviously in a situation that's done virtually, I will do the lab for you. You will end up getting little videos showing you the parts of what that you would be doing if you were here in person. And I also will send you a bunch of data, measurements, weights, and eventually images of what we have. And hopefully you'll get a little of something out of this. So when you write your lab report, you'll have just more data and know a little bit about the journey of where the samples came from. Okay, thank you very much, and I look forward to continuing this lab with you.